There are countless beautiful landscapes and natural phenomena embedded in nature that leaves us awestruck. Today, we find ourselves on a stunning island. Meet Timmy, a nature lover who spends his time trying to comprehend the physics and mathematics behind the workings of the natural world. The island features a stunning beach with mesmerizing waves. It is a delightful afternoon to be here. Timmy has noticed an interesting occurrence. The ocean appears crystal clear near us, but as we look further away, it turns blue. Why is this happening? Why can't we see through the ocean water at a greater distance? The ocean water becomes clearer when our waving angle changes. This phenomenon is known as Fresnel effect. Let's take a closer look at how this phenomenon works. Timmy is now engrossed in deep contemplation about the phenomenon. He desperately needs someone to explain the phenomenon to him, as well as provide guidance on how to model a mathematical formula for it. Luckily, we have QB with us on this island. However, do you know where QB is? Ah, there he is, but seems to be in a deep sleep. Hey QB, could you please wake up? Timmy needs your help with the question. Great news, QB has woken up. Hello QB, could you explain the Fresnel effect to Timmy? The Fresnel effect is not limited to the ocean. It can be observed on any surface that has reflective properties. For example, take a look at the reflection of QB on the table surface. As the viewing angle increases, the reflected image becomes clearer, while it appears dimmer at steeper angles. Similarly, the sky is reflected more, making it appear bluer at wider angles of observation. Let's dive into the physics behind the Fresnel effect. Picture a scenario where a beam of light is directed onto a surface. When the beam strikes the surface, it bounces off in a specific direction, which is determined by the normal vector of the surface. The normal vector is always perpendicular to the surface it's on. The intensity of the reflected light varies depending on the angle between the light vector and the normal vector. When the angle is zero, meaning the vectors are almost parallel, the reflected light has the strongest intensity. However, as the angle increases, the intensity decreases gradually, reaching zero at a 90-degree angle. The surface of the object appears brighter at its center and darker at its edges. This is also called diffuse lighting model. This is the reason we are able to see the surface clearer at a shorter waving angle. This effect can be calculated using the formula magnitude of the light vector multiplied by the magnitude of the normal vector multiplied by the cosine theta. Here, theta is the angle between the light and normal vectors. When the angle is 0, the cosine of theta is 1, and as the angle approaches 90 degrees, the value approaches 0. This formula is also known as the dot product of the two vectors. However, the Fresnel effect is just the opposite of this model, where the reflection is greater at the edges and lower at the center of the sphere. To calculate this, simply subtract the value from 1. Since the dark to light values ranges from 0 to 1, subtracting the value from 1 will give the opposite effect. Note that the appearance of this phenomena is influenced by the angle at which it is viewed. Therefore, we substitute the light vector with the wave direction vector to create the desired effect. To achieve narrower edges, we need to increase the power value. This gives the formula for the Fresnel effect. Wonderful. We have finally grasped the concept of the Fresnel effect and how its formula is derived. QB has been incredibly helpful in aiding our understanding of this topic. As a token of our appreciation, we would like to extend our gratitude to QB. We look forward to seeing you again in the next video where we will be exploring more exciting topics. Thank you.